Romain, and we'll talk about this joint work with Raphael that builds on this, that continues in this line of work.
Hi everyone. Yeah, thank you for inviting me. Thanks for the organizers. Great pleasure to be here. Yes, I will be giving the second part of this circularity-based I/O series of talks, and this is joint work with Raphael Pass. So recall that, as you explained, I'll explain our work with the following in light of the following blueprint. To get I/O, you can go through split FHE that gives XIO that can be bootstrapped to I/O. Okay, and recall that split FHE, it's an FHE. So if you have an encryption of a message, you can evaluate a function on it, and you get an encryption of the function f evaluated on the message. And you can release, essentially, think of it as a randomness, so like a hint for this particular evaluated ciphertext, which has to be succinct. Its size doesn't depend on the size of the output of the function, f of m, and it reveals only f of m, essentially, roughly speaking. Okay, so we've duly covered it. This is the abstraction I'll be using in this talk as well. Okay. Right, so what is our result? Basically, we build I/O from two assumptions. First, the standard learning with error assumption, and second, a strong circular conjecture with respect to standard LWE-based encryptions. Let me explain a little bit more what I mean by this circular conjecture. So in general, circular security say that if you have that security is going to be preserved in the presence of an encrypted key cycle. For instance, you have two encryption schemes, a black one and a blue one, and you consider in particular semantic security of the black scheme. A natural assumption is to say, well, okay, this semantic security is going to be preserved even in the presence of these encryptions here. So here it's an encryption of the blue key under the black scheme, and here encryption of the black key under the blue scheme. Right? You can think of cycle of different sizes. Right? And as I said, the conjecture is to say, well, for natural schemes, semantic security is going to be preserved in the presence of an encrypted key cycle.
Probably conjecture is too strong of a name for the, I mean, too formal of a name for this, but maybe you could say
heuristic?
Heuristic, yes, maybe it's a better name because it's not really a formal conjecture.
Right, design principle or heuristic maybe is a better name. Okay, yeah. Right, so I said natural schemes because this heuristic we know is not true for some particular schemes. There are some schemes that are semantically secure, but not circularly secure. However, all the counterexamples that we know of are contrived. They are specifically designed for circular security to fail. And it's a reasonably widespread assumption to say that for natural schemes, this security is preserved. And the most famous example of this is probably bootstrapping by Gentry, which is the way that's used to obtain unleveled FHE. Right? Unleveled refers to the fact that you can evaluate arbitrary depth circuits and not without any a priori bound. Okay, it requires here in this case a cycle of size 1 actually. And for this application, semantic security suffices. But in general, you may want to consider different security notions. For example, I don't know, like CCA security, leakage resilience, and so on. So this leads to the natural strengthening of this heuristic. Say for any natural schemes and any natural security notion, this security notion is going to be preserved in the presence of an encrypted key cycle. Right? This is a strong circular heuristic that we'll be using. Right, so now let me rephrase our result a little bit more precisely. We can get I/O from LWE and this strong circular heuristic with respect to a new security notion, which we call shielded randomness leakage security, SRL, which roughly speaking involves an adversary that gets a challenge ciphertext and some information about the randomness used to produce the ciphertext. I'll be more specific later. And with respect to two standard encryption schemes, the well-known Gentry, Sarai, and Weathers FHE, fully homomorphic encryption scheme, and a packed variant of Regev encryption scheme, both of which are known to be secure under LWE assumption. More in detail, we first show that GSW is SRL secure from the LWE assumption. And then we show that if you assume this SRL security of GSW is preserved in the presence of a GSW and packed Regev key cycle, and you also assume LWE, then you get IO. So now let me explain what SRL security is in a little bit more detail. So you have an FHE, which encrypt bits. So you have a bunch of encryptions of bits. You can homomorphically evaluate the function f. You'll get FHE of f of m. So basically, the homomorphism says that when you act on the ciphertext, it will act on the plain text, but it will also act on the randomness. So you can think of this encryption as an encryption under a randomness r sub f, because it depends on the function f. And you can actually compute this r sub f directly from the original messages and the original randomness. And you can open this evaluated ciphertext using this r sub f to recover f of m. Right. So this is a property we refer to as randomness homomorphism. And GSW satisfies this property. So once you have a ciphertext, you can decrypt it, usually, as usual, with the secret key, or you can open it with this evaluated randomness. And that doesn't require the secret key. What is SRL leakage? Essentially, it's a shielded variant of this evaluated randomness R sub f for some functions f. The first thing I want to say is, since RF allows to open the ciphertext to recover f of m, and this is also true for shielded variant of RF, we need to restrict the class of function f for which we reveal such leakage. If we want to hope to prove any meaningful security notion, we need to hide some information about the message m. So if you can recover f of m for any f, there's no way. So we will restrict our attention to functions f, which for now I'll call predictable. I'll be more specific later on. Think of them as constant functions. It's a bit more complicated than that, but basically functions whose outputs can be revealed without harming security. And the second comment I want to make is that even if you restrict to, let's say, constant function, revealing RF is not okay. You need a shielded variant of RF. You need to, right. Why is it not okay? It's actually broken. It's not known to be, well, it's insecure if you give out just RF. So you need to shield it. Again, I'll be more specific later. All right. And so with the shield, again, we can prove this is achieved by GSW from LWE. All right. Just some notation. I will actually, it's convenient for me to write vectors like this. Don't be confused into thinking that this is a string encryption. It is a bit encryption. GSW is a bit encryption. It just means it's a concatenation of many base encryptions. All right. All right. So now let me give you the security game, which defines SRL security. So far, it's just an in-CPA security game that we all know, with the differences that actually make it explicit. I make explicit the fact that here the adversary chooses not just one pair of messages, but many of them. All right, and he gets back many challenge ciphertext. This is important because the randomness leakage will be on all the randomness used by all these encryptions. To get this leakage, the adversary will interact with an oracle, leakage oracle, and it goes like this. First, the oracle sends a fresh FHE encryption of 0, upon which the adversary can choose a function f and a prediction alpha. And if the prediction is correct, which means f on the challenge plaintext is equal to alpha, which essentially means the adversary already knows the output, then it's actually okay to give him back the actual leakage, which is R sub f, computed as I showed you before. So it's like homomorphic, it's evaluated randomness computed from this guy here, plus this R star. So if you only look at the leakage, essentially it's RF with a one-time pad, padded with R star. So this looks good. This means no information whatsoever will be leaked about RF. However, this R star is some information about R star is revealed when through the FH encryption of 0, because it uses R star as a randomness. Okay, so this is not equivalent to CPA. And if the prediction is not correct, then the leakage is just bought, and in that case, we say the adversary fails. This can be done many times by the adversary, and at the end, the adversary has to guess which message were encrypted, okay? And he wins if he guesses correctly, and if he didn't fail, if he didn't make the Oracle output bot. And we say a scheme is SRL secure if no efficient adversary can win with probability significantly better than 1/2. And recall that we prove GSW is SRL secure under LWE. All right. Now, to get IO, we actually need a circular variant of this, which looks like this. It's essentially the same thing, except now we have this encrypted key cycle. So not only do we have an FH encryption of the challenge message, but we also have an encryption of the blue secret key under the black scheme, and an encryption of the black secret key under the blue scheme, right? Cycle of size 2. And the evaluated randomness that's part of the leakage will touch the randomness used to encrypt MB, but also escape bar, everything, all the randomness, right? So now so that changes the condition like this, right? Essentially, right. Apart from that, this is the same game. And we show that assume LWE and assume GSW, FHE, and PACTREGEV are circularly SRL secure, according to this definition here, then you get IO.
Romain?
Yes.
Just to play the devil's part. So you started by saying that it's very hard to come up with something which is not circular secure, and I totally agree. You have to work hard. How hard it is to come up with something that violates this security definition?
Well, the only example we know are the one that are used to prove the one that are used to prove bit encryption, so that they will be using lockable obfuscation or like compute and compare. Okay. This is only one we know. And even
in terms of this kind of test, this thing seems to satisfy the I don't know, the heuristic suggestion from your first slide, like that. I mean, you believe that this thing is I don't know, as believable as some standard cyclic security?
Well, so there are some differences. It's not exactly, it's a more sophisticated notion, but sure, like the reason we believe security, like this, I think it fits the general design principle in the sense that I would be surprised, like the only counterexample I can think of, at least, are highly artificial. Essentially, as artificial as for bit encryption. Even though the SRL notion is new, right? I would say, I don't know, like philosophically, yeah, the gap between, yeah, I don't know, like.
Okay, that's good. Just
okay.
Don't have anything formal to say.
Yeah.
So
and Benny, a priori, it could also be like somewhat harder to actually get a counterexample, because to get a counterexample, you actually need to get a scheme that is SRL secure, right?
To begin
so
with,
your
yeah.
starting scheme needs to be SRL secure and not circular SRL secure.
Yeah,
whereas to get a counterexample for semantical security, it's enough to get a scheme that's semantically secure. So here you actually need to start off with. So really, it's only one of the counterexamples for circular security that works for SRL. The most recent one by Daniel, and on based on lockable obfuscation. The earlier ones, we don't know how to modify.
Yeah.
So less of the counterexamples for circular security apply for this notion, because you start off with more.
Yeah.
So just to expand, I think it would also be interesting, and there also it doesn't seem trivial. to have counterexamples which are plausibly circularly secure but broken with SRL security. But there also we do not seem to have clean examples that do that. Even assuming IO, I mean, maybe one can do that, but probably one can do that. But it seems hard to come up with directly.
Like the way I see it, you know, this kind of I think that the word shielding is kind of misleading. This is basically correlated randomness, right? Once you put this R plus R star on the table, then it means that you encrypt the two things under correlated randomness. And I think that the same heuristic feeling that we have about circular security, we could have with respect to this correlated randomness kind of games. What's not clear to me is that what happens when you mix all these things together plus homomorphism, whether it makes, I don't know, makes the assumptions less believable. But I guess that we don't know. I don't know.
It's also another thing is, I'm just confused a little bit by this security game. The adversary doesn't win at all by, is it the case that if the adversary sends a message per F alpha, then the adversary must be convinced that F of MB has to equal alpha, because otherwise they fail? Because if so, then why wouldn't the adversary, why doesn't it just reduce to the case that the adversary always just use F as the constant zero function and alpha as the zero value, and then basically all that the adversary does is just get a bunch of encryption of R star plus this, I guess the point is that this is RF plus R star. So yeah, that's the thing that somewhat confuses me.
It wouldn't work, like, it wouldn't be sufficient to build IO if you had actual constant function. That's why I said you can think of them as constant function. They're not. So even though the output is predictable, it's alpha, it's known by the adversary, the behavior of F will depend on its input. In particular, if F is given an input, something that doesn't contain escape bar, it will not output the same thing as if it actually is fed with something that contains escape bar. And I think this is why, maybe Daniel is going to mention it, this is why this type of assumption is qualitatively different, because so F is not constant. That's the first point I wanted to make. Second point is also, you cannot actually switch, as is sometimes done, FHE, like basically a cycle of keys, an encrypted key cycle to encryptions of 0. This you cannot do it because for the function we care about to build XIO, you can detect. You will basically lose correctness. I'm not sure it's exactly answering your question, but I think it's a good point to make.
Okay. I think makes, yeah, but maybe I understand better as you continue.
So just regarding your last point, sorry to interrupt.
Yes.
So if you go back to the heuristic, well, actually this is also based on discussion that I had with Zvika. So I could rephrase your heuristic in the following way. I could say for normal schemes, the adversary cannot even tell whether there was a cycle or there was no cycle, and this is the reason why it should remain secure. And this kind of argument you cannot apply here, right?
Yes, because here you could decide, yes, exactly. This kind of argument you cannot apply. We don't need it. That's also the thing, right? But yes, we cannot apply this argument.
So it's slightly different setting.
It's a slightly different, qualitatively different, yes. But technically, assuming SRL security is preserved in the presence of an encrypted key cycle, as Raphael said, it's incomparable. Technically incomparable to assuming that semantic security is preserved in the presence of an encrypted key cycle. You start off with a stronger security and you end up with a stronger security.
Sure.
But there are subtleties for sure. That some of the intuition you may have on circular security will not actually hold here. Yeah.
Good.
All right. And just maybe, okay, that's maybe too much, but like you said that, I don't know, that you can think of it as a correlation intractability, correlation type of assumption, like saying, well, so the thing is, even in the plain SRL security, you have this correlation, right? You have this thing here and that guy here, which are correlated. And this you can actually prove under LWE. So the gap is really between when you add up this circular thing. Otherwise, you can actually prove.
Very good.
Okay. All right. So the reason, yeah. So we think it's a natural security notion, and let me show you with an application of plain circular security, SRL, not circular. Sorry, I say plain circular. I mean plain, no circular. All right. So an application where this leakage can show up, like a toy example. So you have a database of private record, let's say bank record, and you trust Alice, a third party, to encrypt it for you and put it in the cloud. It's mfetch encrypted. And Alice will also compute an mfetch encryption of 0. And then at some point, someone asks you to prove a statement on your database, for example, that you have enough money on your bank account. And without, of course, you don't want to reveal the exact amount of money you have. So you will ask Alice to produce a zero knowledge proof. And Alice can just send the SRL leakage as a proof. It's short, it doesn't depend on the size of the complexity of the statement. And everybody can verify that this proof is holds. We can verify this proof by FHE evaluating this encryption here, and then adding the encryption of 0, and then opening the result with the SRL leakage and checking the result. So this is sound as long as the encryption produced by Alice are proper. And without going into the details, because actually it will require simulation-based SRL security notion, zero knowledge is achieved by SRL security. Right? Essentially, the SRL leakage only reveals F of database. All right, and Alice can provide many proofs, and the online phase is super short. It's just a SRL leakage, right? And Alice has to pre-compute all these encryptions of 0. All right. So just like to give you a sense where this SRL can show up. Okay. So again, just repeating, our result is to be the IO from this assumption, and I'll focus in the rest of this talk on the second part, namely showing IO from LWE plus this circular SRL security. And we build upon the BDGM20A split FHE. We did not actually build a split FHE, but for the stock, I will explain it using the abstractions that Yulo explained. All right. So remember, the way they build a split FHE is start off with any FHE and evaluate a function on it. Then if there's a randomness of the FHE is too large, and it's also insecure to release it. So that's not going to be a good hint. However, there are some LHE, they're not fully homomorphic, they are only linearly homomorphic, for which we have small randomness. First. And second, decrypting an FHE is nothing else but computing linear operation and rounding. So at least we can perform the linear operation of the decryption under the hood of the LHE, not the rounding. So you can perform a partial decryption, like you proxy re-encrypt, you turn this FHE into an LHE. And because you cannot round, you will have some FHE decryption noise. And as Julio explained, we know that now, okay, we could release the randomness of this guy. Now it is short. Great, we have succinctness, but it's still insecure because it will also reveal, in particular, this noise, this FHE decryption noise. And we know that's breaking security. So that's not what they do. They say, okay, now suppose you have this magical oracle, which anytime it's invoked, spits out a fresh LHE encryption of a smudging noise, SI. Now that would be great, because now you can just add this to that. And now you release the randomness of the addition. So this thing here, it is succinct and it is actually secure. They prove it. Because essentially, this smudging noise, well, is gonna basically erase all the information. It's gonna smudge this FHE decryption noise in red. And the challenge is to implement this oracle, right? There's no such thing as an oracle that spits out LHE encryption or smudging noise. So they have to create them. And this is where the heuristic begins. So what do? As basically explaining what you already mentioned, but I think it's good for to make sure. You start out with a random oracle that spits out random bits, right? That okay. Because LHE ciphertexts are dense, any bit string is essentially an encryption. Of course, it's not going to be an encryption of something structured. It's going to be an encryption of something uniform, which is not useful as such. So their idea was to actually proxy re-encrypt it. Basically, you want to round this uniform message UI and make it smaller. You cannot round with LHE, we know that, but you can round with FHE. So you turn this LHE encryption into an FHE. That requires a key cycle, by the way. Then you round. You can do whatever you want. It's an FHE. And then you turn it back again to an LHE. So basically, since you cannot have fresh LHE encryption of smudging noise, you engineer it yourself. You craft it. You create it. And you get an LHE encryption that's not fresh, but that's okay, of a noise that is of the right size. It's a smudging size. It's not uniform. You still get some meaningful information, but you can smudge the annoying FHE decryption noise in red. But when you do this proxy encryption, again, you will create an FHE decryption noise again. And so it's going around a little bit in circle because you essentially create a smudging noise to erase an FHE decryption noise, but doing so create an extra FHE decryption noise. Right. And the problem is these actually are dependent. They are correlated statistically. But the idea is, in practice, we don't really know how to exploit these correlations, right? And so heuristically, it is okay. There's no way to break this in practice. And in fact, in the paper, they even show extra like heuristics to make it even harder to potentially exploit. All right. So this is what I did. And our work will basically be to instantiate this thing with a provable secure, with a security proof under the circular SRL assumption. All right, this is our contribution. So the first thing we'll do, that's not too hard, is just replace the random oracle by a CRS. We can afford it because we know XIO with preprocessing is sufficient. First observation, quite simple. A second more important thing is to say, the problem is this correlation, right? The fact that FHE decryption noise depends on the evaluated plain text. They are correlated. So what we do is refresh the FHE evaluation. This is common if you want to obtain circuit privacy. If you want, the idea is to get an FHE evaluation which looks like a fresh encryption. So that's great. That's exactly what we want. It would break correlations. However, this evaluation now becomes randomized, and it's important to reveal the random coins that are used to refresh the FHE ciphertext, because you want the person that obfuscates and the person that runs the obfuscation to agree. They want to actually compute the same ciphertext so they can actually recover the output. So you need actually to reveal these random coins. Now it may seem a little bit dangerous. You refresh, but you reveal the random coins used to refresh. And so this alone will not be enough, right? It's not magical. However, it will be good. It will be useful anyway to locally break the correlation. And then you can essentially conclude the proof with this SRL circular security assumption that I showed you before. All right, the combination of these two will actually provide proof. So this is how it looks. We've replaced the random oracle by a CRS, which contains a bunch of LHE encryption of uniform noise. As before, we proxy re-encrypt them, we round, and now we refresh. That's a new thing to break the correlation. And now, okay, we will have a fresh FHE encryption. That's great, which means if the FHE encryption is fresh, the resulting noise is also fresh, and therefore it is independent of this guy here, and everything works out. But as I said, that is too simplistic. We need to actually reveal the random coins that are used to refresh. You put them in the CRS. So now you cannot say the noise is fresh. It is actually not fresh. It depends on these random coins. Right. And now actually let's look at how we concretely implement this idea. Refreshing is just adding or subtracting, it's the same thing, an encryption of 0. right? Technically, this is an extra noisy encryption. So these encryptions uses as randomness some kind of noise. It's lattice based. You should not be too surprised, I guess. And this is a much higher magnitude noise. And the resulting ciphertext is going to be under the randomness of the original evaluated ciphertext minus this. So this is randomness homomorphism. Okay. So far, this is not fresh, right? It depends on the function that has been evaluated on it, which I call fi. So we don't want that. So we use the circuit privacy property of the FHE, which says that essentially you can make this guy, this thing fresh at the price of making this thing not fresh. You can move around the problem, right? You cannot completely erase all the circular issues that are come up, right? But you can locally, you can at least make this FHE fresh, which means this thing will not be fresh because it depends on this, but it will be independent from the crafted smudging noise, which is exactly what we want. Okay, so now this part is good. This part is good. We have to take care about that part. And if you look at it, right, you will notice maybe that this looks exactly like an SRL leakage. It is actually, right? It's an evaluated randomness padded with some fresh randomness. This should be an encryption of 0. It is, you can generate this guy from an encryption of 0. Doesn't really matter how. So trust me, this is just an SRL leakage. So this is how you conclude the proof, by using SRL Circular Security. All right. So, right, the conclusion is the result again, IO from LWE. And by the way, because we need smudging, not too surprisingly, we need a sub-exponential modulus to noise ratio. All right, and we use a strong circular security conjecture, which has some qualitatively difference with the circular conjecture. I use conjecture, but think of it as heuristic that we are used to. It's qualitatively different, and it's with respect to this new SRL security and this well-known scheme, GSW and packed reggae. Okay, which both of them are secure under LWE. All right. So originally, actually, what we did is the same thing, but we used Zurich, which is secure only from a factorization style assumption. I mean, decisional composite residuosity. Later on, independently, BDGM20B and ourselves, we replace essentially this linear homomorphic encryption. So they used packed dual regev, and we use the packed regev encryption. At the level of details of my talk, the differences between these two works are not major. They rely on a similar type of assumption, right? To key or key randomness cycle. Okay, so similar kind of circular SRL assumption. All right, and then there's the work of with Tekwi and Daniel Wicks that you will hear in a couple of minutes, which also has a circular flavor. It relies on an assumption known as oblivious LW sampling. They give a security proof under this assumption, and they also give a heuristic construction of this oblivious LW sampling. I mean, I'm not going to talk about it. And all of this work, they rely on the blueprint that Giulio showed, actually, this BDGM20A. And they inherit from this original construction the conceptual simplicity, right? There's no, yeah. And finally, this is not this first work with Zurich, but all of this other work, they are plausibly post-quantum secure. That's another advantage. And I'll conclude with a few words on SRL Circular Security, but we already actually talked about this. So it's so the heuristic is qualitatively different, and the SRL security assumption is qualitatively stronger than the plain circular security. But we still think it's a natural security notion, which we can prove without key cycle. So the confidence we have is backed up by a general design principle. All right. So yeah, that's it for me. Thank you very much. Let me know if you have questions, if we have time.
Thank you. Thank you. We do have a little bit of time for questions. So are there any questions? And yes, I see. According to the so according to the schedule, I think Daniel, you talk only needs to start at 12:15. 12:15 Pacific, but we could start it maybe a little bit earlier if you wanted just to be more on the safe side.
Either way is okay. There should be enough time if we started the.
Okay.
Yeah. Just in case, I guess people saw the schedule ahead of time or want to come.
Yes. So we can stick with the original schedule. Yes. Yes. I'm not completely sure. Yeah, I think I might have screwed up a little bit with the schedule. I didn't. I think I didn't intend this particular break to be that large, but maybe it's a good thing we all could use a break. So so we can meet up at 12:15 on Pacific, which is 3:15 Eastern.